Hello and welcome to my talk, Human-in-the-Loop Automatic Program Repair. This is a paper published at ICST 2020. My name is Marcel Böhme. I'm a senior lecturer here at Monash University in Australia. And this work is in collaboration with Charaka at Monash University and Tuan, who has now moved to University of Melbourne in Australia. So our problem is test-driven automated program repair, but without the tests. So in test-driven automatic program repair, you're given a failing test suite. That means at least one test case is failing. And then by some automated means, you have to change the program such that all test cases pass. So a common approach to that is search-based automated program repair, where you would first generate a repair candidate. Then you would use the test cases to localize potential repair sites in the program, and then change one or more of these repair sites in some way to generate a repair candidate. Then in order to evaluate or validate the repair candidate, you execute the test suite again and count the number of passing test cases. And if more test cases pass, you can use this candidate for the next iteration and improve on that. And if all test cases pass, you have successfully repaired your program with respect to the test suite. But then you might wonder, isn't that overfitting? I mean, what about the test suite? The quality of the generated repair strictly depends on the quality of the test suite. So if I have a bad test suite, then I have a bad repair. And what is worse, what if no test suite is even available at all? So if there's just a user who comes and reports a bug, can we even automatically repair this program? So existing approaches to that problem, where no test suite exists, leverage the existence of an automated oracle. So an automated oracle is something which can tell whether an execution reveals a bug or not. Say you have a crash. So you generate inputs that crash, that you can automatically change the program such that the program doesn't crash for these inputs anymore. But what if you don't have such an automated oracle either? So we only have semantic bugs. We have a user who is reporting the bug. And what do we do then? How do we automatically repair in an interactive way by asking the user questions about the bug? And this is what Learn to Fix does. It negotiates with the bug reporting user the condition under which the bug is observed. So then when the budget of queries is exhausted, it attempts to repair the bug. Now, by systematic queries, Learn to Fix learns an automatic bug oracle that becomes increasingly more accurate in predicting the user's response. So one example of such a query is, when executing this alternative test input, we see the following behavior. Is the bug observed? And the user just says, yeah, that's what I expect or not. Yes or no. And Learn to Fix learns a condition or automated bug oracle, which could look like this. The bug is observed only if the input is an equilateral triangle with sides of unit length. So this is a general condition applying to several inputs, right? So then our hypothesis is that a machine that can classify more accurately which inputs are bug revealing and which are not, can also auto-generate repairs of better quality. So then our key challenge is to maximize the accuracy of that oracle in predicting which test cases are failing, given only a small budget of queries, like 20 queries. So here's an example. So this is the classical triangle example that you find in software testing textbooks. So you're supposed to implement a function called classify, which takes 3 inputs that represent the length of the sides of a triangle and returns an integer which represents whether the triangle is equilateral, isosceles, scalene, or it's not a triangle at all. So here's an implementation which is buggy. So we see, for instance, if the integer values for these three sides are negative, there's an invalid triangle. If these three sides don't add up so a is less than equals, one side is less than equals the third side minus the second side, then the triangle is invalid as well. And then we come to the standard cases, like equilateral, classifying equilateral triangle. The developer writes A equals B equals C. Now in C, you can't do this. In C, what happens, it interprets A equals B as true and writes a 1 here. And then it compares this 1 to the third variable C. So this is a bug. So what happens is if we pass in 2, 2, 2, it would return isosceles even though it is an equilateral triangle. Just because 2 equals 2 is true is 1, and 1 equals 2 equals 1 is false. So it would go to the second statement, to the second condition. So to be more general, this program returns an unexpected output for all equilateral triangles except 1, 1, 1, and for all isosceles triangles where the third side of the triangle is of the unit length is equals 1. So we learn to fix generates this automated oracle as an SMT formula over the inputs. So why SMT? We think that SMT is a good representation of program semantics. It's used in automated program repair and semantic program repair, and it's used in symbolic execution. So it kind of represents this discontinuous behavior in programs, unlike something like a support vector machine, which would also be a classifier, and it works with integers, but it cannot represent this discontinuous behavior of programs. So we learn an SMT formula over the integers, actually over the numerics, like including floating point numbers. So what are the ingredients of learn to fix? Firstly, we use mutational fuzzing. So we take that one failing test case and generate more failing tests, hopefully more failing test cases, or generally more test cases in the neighborhood of the failing test case. So we take that 2, 2, 2 and substitute 1, 2 by a 3, or substitute all 2s by all 3s. So using some mutation operators, we explore the neighborhood of this failing test case. This is an easy thing. Fuzzing is very established. Then we use active learning to construct this constraint. And I'm going to come to the details of that later. And once we have labeled test cases, we then use plain old test-driven automated program repair to auto-generate the repair from these labeled test cases. So we'll focus on active learning. So let's just do a little bit of terminology. A test is a tuple, which is an input vector and an output vector. Where the input vector and output vector are numbers. And a labeled test case is user classified tests that is either passing or failing. Now, given a set of labeled tests, we use a tool called incall, which learns this SMT constraint, satisfiability modular theory, linear something arithmetic constraint. So this is essentially over linear arithmetic over numerics that is satisfied by all failing tests, but by no passing tests. So there's no approximation. It's really a boundary between failing and passing tests. And we extend this passive learning into an active learning, where learn to fix is the learner, the user is the teacher, and the learner queries the teacher about the labels of the most informative samples. Not about all samples, the samples are tests, but the most informative ones. So how do we maximize the oracle accuracy, given only a limited budget of queries? So what we do is we maximize the probability to present to the user failing test cases. And this is to reduce the labeling effort. So we can't present all generated test cases. The user just doesn't have the time to label all of them. And it also addresses the class imbalance problem. So a test case is much more likely to be passing than it is failing. So by increasing the probability to present failing test cases, Learn to Fix also better learns to identify such failing test cases. So how do we even know this failure probability before we even ask the user? We don't have the label for that test case. We don't know whether it's actually failing. How do we compute the probability? We have an automated oracle that we just learned, but it's only binary. It can only tell you whether or not the bug is observed or predict whether the bug or not is observed or not. So what we do is we construct a so-called unbiased committee of classifiers from our oracle. And then we ask this committee for a given test case to classify. And the proportion of classifiers labeled T, this test case as failing, will become an estimate of the failure probability for that test case. And if more than 50% of the classifiers rate that test case as failing, we just say it's likely failing. So here's that algorithm to decide whether or not to send a given generated test case to the user for labeling. So it takes the test case and test case as input, an automated oracle as input, and the committee size. Firstly, we ask the oracle. If the oracle says it is failing, then we return true. The user should label this. We want to be conservative, right? So if it says predicts passing, it could be wrong. So we ask the committee, how do we construct this committee of classifiers? What we do is we fuss again this unlabeled test case to generate more test cases in the neighborhood of that test case, and then hypothetically assume both labels for that test case, passing and failing, and generate two oracles for both conditions for this one failing test case. And learn that corresponding oracle and ask these corresponding oracles. If any of those marks it as failing, we increment this votes variable, which is initially set to 0. And then we simply take the proportion of votes to 2 times the committee size as this probability estimate that the test case is failing. And if this estimate is greater than or equals 0.5, we return true. The user should label this test case. So here's a more architectural overview of Learn to Fix. You have you start with a failing test case, which is added here. We also have a buggy program. Then we fuss that test case and we learn the SMT formula first, and pass this failing test case to that oracle, automated oracle. If it's labeled as failing, if it's predicted as failing, the human labels. If it's not predicted as failing, we ask our supporting oracle committee. If the committee predicts it as failing, we again ask the human to label. Otherwise, we just discard. Now, all these labeled test cases will go into the test suite, and only failing test cases will then fuss further in the next iterations. So this generated and labeled test cases will then be passed to the repair tool, which then generates the patch. So we conducted an experiment, and we used code flaws as our repair benchmark. It comes with a lot of programs, complex programs from programming contests of a lot of users and code forces. And we selected a subset of those programs that contain at least one failing test and only take numeric inputs. At the moment, our repair approach is focused on numeric inputs. Now, each program comes with a buggy version and a golden version. So we'll later say that we'll later use this golden version as our oracle, as our human oracle for our experiments. There are also manually written training test cases, which are used for a repair tool to repair the program. And there are held out test cases, which are often used validate the generated repair. So we select a random failing test case from the training set. Then in order to label, we use the golden version. And if you want, you can reproduce our experiments because we all publish all our artifacts on GitHub. So the first question that we ask is, how accurately does Learn-to-Fix Learn Automatic Oracle label the repair benchmarks failing tests? So how good is this Oracle that we generated, that Learn-to-Fix generates? So here we see labeling effort. So we have, the users will answer at most 10 questions, at most 20 questions, at most 30 questions. Is this a failing test case or not? And this is the prediction accuracy, which is measured as the manually labeled test cases, the labels of the manually labeled test cases correctly predicted, the proportion of those manually labeled test cases where the label is correctly predicted. And we see that even though Learn-to-Fix has only ever seen just a single failing test case from this manually labeled validation test, Learn-to-Fix, the automatic Oracle that Learn-to-Fix generates, is able to accurately predict the label of 75 to 84% of validation tests for the median subject. So this is across subjects, across all 500 something subjects. Even for the minority class, which is the failing test cases, at least 78% of failing validation tests are correctly labeled for the majority of subjects, which is high conditional accuracy. Now, human effort, so our second research question. What is the proportion of generated test cases that are actually sent to the user? What is the proportion of generated test cases that are discarded? We can see that there, as the labeling effort, prediction accuracy increases, labeling effort increases, less test cases are actually sent to the user. This is because the user, because the automated Oracle can label, identify the label correctly itself, accurately as already. So the user is asked to label a smaller proportion of generated test cases. Yet the user is asked to label roughly the same proportion of actually failing test cases. So it's, even though overall the user receives less test cases, proportionally, it receives the same proportion of failing test cases, right? So the other thing is that as the prediction accuracy of the automated Oracle increases, the probability that the user is asked to label a test that is indeed failing also increases. So the probability to label a failing test case increases, even though the probability to generate a failing test case does not decrease. It does not change. So what about patch quality? What about the patches that are now generated with these test suites that we generated through learning the automated Oracle? So one insight is that repairability, the success of generating a repair that passes all tests, all training tests, reduces as we increase labeling effort. So we can generate less repairs than the manual test suite, than using the manual test suite. But the quality of the repairs that we actually are successful in generating increases. So the validation score is the percentage of head-out test cases that pass. For the manually generated test suite, on the median, 2.4% of head-out test cases do not still fail after the repair, right? On average, 14.9%. For our auto-generated test suite, 0% on the median, that means for the median subject, 0% of validation head-out test cases still fail. On average, 10.3%, which is much less. So our repairs are better because less head-out test cases still fail. So what I've explained today is that we can do test-driven automated program repair even without tests by involving the user and interacting with the user. I've explained how we generate queries, systematically generate queries to the user to learn an automated oracle that becomes increasingly more accurate in predicting the user's response. And I've also explained just how this active learning works and gave you some evidence, some empirical evidence of this being an accurate learning and with low effort for the human. Thank you.